Welcome to this advanced lecture on one of the most fascinating phenomena in modern nanoscale heat transport, near-zero and apparently negative thermal conductivity. In conventional materials, heat flows from hot to cold regions through phonon transport, but in nanostructures, something extraordinary can happen. Let's begin by reviewing classical Fourier heat conduction to understand what makes nanostructures so different. Fourier's law states that heat flux Q equals negative kappa times the temperature gradient. Here kappa is thermal conductivity. In all bulk materials, thermal conductivity kappa is strictly positive, ensuring heat flows down the temperature gradient. Thermal conductivity equals 1/3 times specific heat C times phonon velocity V times mean free path lambda. Here's a typical temperature profile in bulk materials. Temperature decreases linearly, and heat flows uniformly from left to right. For reference, typical bulk thermal conductivities are quite substantial. Copper has thermal conductivity around 400 watts per meter Kelvin. Silicon has thermal conductivity around 150 watts per meter Kelvin at room temperature. When we shrink dimensions to the nanoscale, fundamentally new physics emerges. A key question: what happens when the structure size becomes comparable to phonon wavelengths or mean free paths? When the structure length L is comparable to the phonon mean free path lambda, ballistic transport dominates. In a superlattice structure with alternating nanolayers, phonons scatter at every interface, drastically reducing thermal conductivity. The effective thermal conductivity is reduced by a factor of 1 plus lambda over L, where L is the layer thickness. Phononic crystals take this further by creating complete band gaps that block phonon propagation. A phononic crystal consists of a periodic arrangement of inclusions that create forbidden frequency bands for phonon propagation. The phonon dispersion relation shows omega squared equals K over M times 1 minus cosine of Q times lattice constant A. These band gaps completely block phonon transport at specific frequencies, creating ultra-low thermal conductivity. This dispersion relation shows the phonon band structure with a highlighted band gap where no propagating modes exist. In experimental phononic crystals, we can achieve remarkably low thermal conductivities. Thermal conductivity in phononic crystals can be as low as 0.1 watts per meter Kelvin, 3 orders of magnitude below bulk silicon. At the nanoscale, Fourier's law itself breaks down, leading to non-Fourier heat transport phenomena. Why does Fourier's law fail? Because it assumes local thermal equilibrium and ignores the finite phonon relaxation time. The Cattaneo equation introduces a relaxation time tau sub q, giving tau q times partial q over partial t plus q equals negative kappa grad t. The relaxation time tau q equals lambda over v, typically around 10 picoseconds for phonons. The heat flux can exhibit transient oscillations, with the flux temporarily reversing direction before settling to steady state. This oscillatory behavior is where apparent negative conductivity appears during the transient phase. To rigorously understand nanoscale heat transport, we need the Boltzmann transport equation. The Boltzmann equation states partial F over partial T plus versus dot grad F equals the collision term, where F is the phonon distribution function. For phonons, we must solve this equation for each frequency mode, accounting for different scattering mechanisms. Thermal conductivity becomes a sum over frequencies, 1/3 sum over omega of C omega times versus omega times lambda omega. Phonon transport transitions from ballistic at short-length scales through a transition regime to diffusive Fourier transport at large scales. Now let's see how we engineer structures with ultra-low, near-zero thermal conductivity. Strategy 1. Maximize interface scattering by creating many interfaces in superlattices. Perpendicular conductivity equals 1 over the sum of layer resistances, di over kappa I, plus interface Kapitsa resistances, Rk. Strategy 2. Introduce nanoscale porosity to scatter phonons at void boundaries. A porous nanostructure with periodic voids creates strong phonon scattering, reducing thermal conductivity by an order of magnitude. Porous conductivity approximately equals bulk conductivity times 1 minus porosity phi to the 3/2 power. Strategy 3. Use alloy scattering where mass disorder scatters high-frequency phonons. The alloy scattering rate is proportional to frequency to the fourth power, strongly affecting high-frequency phonons. Now we arrive at the fascinating phenomenon of apparent negative thermal conductivity. Can heat really flow from cold to hot? Not in steady state, but transient and non-local effects can create this appearance. The heat flux involves a memory integral. Q of xt equals negative integral of kernel K times temperature gradient at earlier times. During transient response, the heat flux can temporarily become negative before the system equilibrates. This occurs because phonon transport exhibits wave-like behavior at short timescales, not diffusive behavior. The phonon heat equation becomes wave-like. Second time derivative minus versus squared Laplacian plus damping term equals 0. Let's examine real experimental observations of these exotic thermal transport phenomena. Measurements in silicon nanowires show thermal conductivity dropping by over 100 times compared to bulk silicon. Silicon nanowires can exhibit thermal conductivity around 1 watt per meter Kelvin, approaching that of glass. This graph shows how thermal conductivity decreases with nanowire diameter d, following the expected one over d scaling. Time-resolved pump probe measurements reveal non-Fourier dynamics with picosecond timescales. When observation time is less than relaxation time tau q, we observe non-Fourier ballistic heat transport. Multiple theoretical approaches are needed to model these complex nanoscale phenomena. Molecular dynamics simulations directly compute atomic trajectories, giving exact phonon dynamics but limited system sizes. The lattice-Boltzmann method solves the phonon-Boltzmann equation on a discrete lattice. Atomistic Green's function methods compute transmission coefficients for each phonon mode through the nanostructure. Thermal conductivity equals h bar squared over kBt squared, sum over omega squared, Bose derivative, times transmission T omega. These computational approaches complement each other, with Boltzmann methods providing framework for molecular dynamics, Green's functions, and Monte Carlo simulations. At low temperatures and small scales, quantum effects become essential in thermal transport. Quantum-specific heat involves the Bose-Einstein distribution with exponential temperature dependence. At low temperatures, only low-frequency acoustic phonons are thermally excited, leading to strong temperature dependence. Thermal conductivity scales as T cubed at low temperatures due to the T cubed specific heat and T-independent scattering. This graph shows the T cubed temperature dependence of thermal conductivity at low temperatures, a signature quantum effect. Asymmetric nanostructures can create thermal diodes where heat flows preferentially in one direction. A graded nanostructure acts as a thermal diode, conducting heat well in one direction but poorly in the reverse direction. Thermal rectification ratio R equals kappa forward minus kappa reverse over kappa forward plus kappa reverse. Experimental thermal rectification ratios up to 50% have been measured in asymmetric nanostructures. Highly anisotropic materials show vastly different conductivities in different directions. In layered materials, in-plane conductivity kappa parallel can be orders of magnitude larger than cross-plane kappa perpendicular. Layered structures show high end-plane thermal conductivity along the layers, but very low cross-plane conductivity. The anisotropy ratio kappa parallel over kappa perpendicular can reach 100 to 1000 in graphite and similar materials. Does negative thermal conductivity violate the second law of thermodynamics? Let's investigate carefully. The second law of thermodynamics requires that entropy must increase in isolated systems. Entropy production rate equals negative integral of q dot grad T over T squared, which must be non-negative. Does negative conductivity violate this fundamental constraint? The answer is subtle and important. No violation occurs because apparent negative conductivity is transient and involves non-local effects, not steady-state behavior. Heat flux times temperature gradient can be negative locally and temporarily, but integrated entropy still increases. While transient reverse flow can occur locally, the net integrated heat flow always goes from hot to cold in steady state. These exotic thermal properties enable revolutionary new technologies. Ultra-low thermal conductivity dramatically improves thermoelectric efficiency by maintaining temperature gradients. Thermoelectric figure of merit ZT equals Seebeck squared times electrical conductivity times temperature over thermal conductivity. Reducing thermal conductivity kappa while maintaining electrical conductivity increases ZT and energy conversion efficiency. Application 2. Controlling heat flow in electronic devices for hotspot mitigation and thermal isolation. Application 3. Thermal metamaterials enable cloaking, focusing, and routing heat flow in unprecedented ways. A thermal cloak uses engineered conductivity to guide heat flow around a central region, creating a thermally invisible zone. Current research is pushing the boundaries of thermal transport control even further. Frontier 1. Topological phononic materials with protected edge states for robust heat transport channels. Frontier 2. Quantum thermal Hall effect, where phonons carry heat transverse to temperature gradient. Frontier 3. Hyperbolic thermal metamaterials with indefinite conductivity tensors, enabling extraordinary heat control. In hyperbolic materials, the product of conductivities in different directions is negative, creating hyperbolic heat flow patterns. Hyperbolic thermal materials create exotic heat flow patterns that resemble hyperbolas rather than circles. Let's work through a concrete numerical example to see the magnitude of these effects. Starting with bulk silicon thermal conductivity of 150 watts per meter Kelvin at room temperature. Consider a silicon nanowire with diameter d equals 50 nanometers. The phonon mean free path in bulk silicon is approximately 300 nanometers. Nanowire conductivity approximately equals bulk conductivity times d over lambda, giving 150 times 50 over 300. This gives us a nanowire thermal conductivity of approximately 25 watts per meter Kelvin.